Hello everyone, I would like to welcome you all for today's lecture. We will briefly look at what we did last time. We looked at some aspects of Claisen rearrangement and their variations in terms of substage structure. For example, the last one that we took was zwitterionic Claisen rearrangement, which was close to the ketene based reaction. Here the substrate was slightly different. For example, if we start with this allylamine and react it with this acid chloride in the presence of a Lewis acid, then what we discussed was that the reaction proceeds through this enolate, and of course it leads to the formation of the corresponding product like this, in which the R2 and R3 groups were anti-displosed. But of course we can take differently oriented this particular double bond, that means cis, and then we can get different stereochemistry in the final product. Likewise, we also looked at the chromium based oxidation, particularly in the enone transposition of this type to this type by introducing an R group here and carrying out the oxidative rearrangement of this kind of tertiary allylic alcohol. This rearrangement was kind of reminiscence of the Claisen rearrangement, and therefore we had a nice way of converting one enone to the other enone by introducing another substituent at the position where the ketone was present. Also, we looked at the Overman rearrangement, where conversion of allyl alcohol to the corresponding allyl amine via a transposition of the double bond was seen, and it was proceeded via trichloroacetamidate. Finally, we looked at the Bamford-Stevens reactions and Shapiro reactions. Say particularly the Shapiro reaction, which we discussed in the end, was basically converting a tosylhydrazone to the corresponding vinyl lithium or vinyl anion. And first we looked at the reaction of this vinyl anion with DMF to form the corresponding vinyl aldehyde. Now it can be possible to make use of this vinyl anion to react with chlorothymidylsilane and generate a very important intermediate, which is a vinyl silane. So today we would like to look at the reactions of vinyl silane and how do they give different types of products. So supposing if we take the vinyl silane, which is made by the method of Shapiro reaction, and if EX is used as it is shown here, is if SiMe3, then we can carry out epoxidation using metachloroprobenzoic acid. And it is very interesting to see that such epoxides, which are basically derived from vinyl silanes, when they are reacted with different nucleophiles, say for example lithium aluminum hydride. So what you have in lithium aluminum hydride is something of this kind. We have here H and minus here and a positive charge here. So this is what the lithium aluminum hydroxide. So this is the hydride, that is what is going to act as a nucleophile. Now it is very interesting to see that there is a regioselectivity in terms of reduction of this particular epoxide, and it opens up in this fashion. So there is no reaction here, but there is a reaction at this center. Now this is very intriguing because the nucleophile actually should be expected to attack on a sterically less inert situation, that is the carbon holding the R1, could be, and also because one could expect some other effects of silicon. But what is happening here is the nucleophile attacks on the carbon alpha to silicon, and it is favored by simultaneous interaction
of the approaching electron pair, that means the hydrogen is approaching with the electron pair with the anti-bonding orbital on the epoxide. So, you have this particular anti-bonding orbital of the epoxide carbon oxygen bond and the vacant 3d orbitals of the silicon. So, basically when this is approaching here, of course, when it is approaching here also it will be the same thing as far as anti-bonding orbital of the carbon oxygen bond is concerned, but here additional factor is that the anion interacts also with the empty d orbitals, 3d orbitals of the silicon simultaneously. Therefore, this hydrogen here H minus tries to interact with the empty 3d orbitals of the silicon as well as the anti-bonding orbital of the CO, and thus it reflects the regiochemistry of the reduction that is observed. This is quite given in much detail in this particular reference that one can look at it if one wants to know a little bit more detail about this particular observations. And now if we oxidize this particular silanol, we can get the corresponding ketone here, and what one can do is if we simply work up this particular substrate here, then you can imagine that there will be desilylation readily happening, and then one can get the corresponding ketone. So, if one looks at it, what we have done it is we started with a ketone, and through the Shapiro reaction we got the corresponding vinyl lithium, and if that vinyl lithium, supposing if we say that the vinyl lithium was something of this kind, vinyl lithium here. So, you have vinyl lithium and that leads to the formation of the vinyl silane, and then that eventually has been converted to the corresponding ketone. So, you can see that the ketone was here, now the ketone has come next to the R1 group. So, this was one carbon away from the carbonyl group. So, this is what is called as 1,2 ketone transposition. So, this is a very interesting application of the silane based chemistry, where vinyl silanes can be epoxidized, reduced, followed by oxidation to convert a ketone into another ketone, and which is what is 1,2 ketone transposition. Now we go for another topic where we try to look at how allyl metal additions are taking place on a carbonyl group. Say for example, if we have a substrate of this kind where we have an aldehyde and we try and take an allyl metal kind of substrate, and if we adapt the double allyl group onto this, we can convert aldehyde into homoallyl alcohol here. This homoallyl alcohol is very useful because you can carry out epoxidation and get an epoxide here, which can allow many more manipulations of the functional groups. You can cleave the double bond here by ozonolysis, and then of course you can get the corresponding aldehyde. You can do the hydroboration oxidation, and you can think about various different types of reactions of the double bond dihydroxylation. We can also carry out something like called as olefin metathesis, which we will look at later on. Of course, cycloadditions can be carried out. You have a double bond, so you can carry out cycloaddition reactions, and you also can carry out hydroformylation reactions. Now, these types of substrate scopes and reaction scopes are numerous, and therefore what is this MXN, or what is M? M can be lithium, magnesium, boron, chromium, tin, silicon, zinc, etc. Many of these things have been studied, and of course depending on which kind of metal has been used, there are different types of reaction parameters, and the stereoselectivity or the regioselectivity depends on various factors of this kind. So, we will look at a few of them in this particular course. Now, if we look at the crotile based reactions, say for example, if we look at something like this here, you have an mx here, then how does this reaction occur? Now, it is seen that usually you have the reaction going via this. That means you have here RCH2 RCHO for example here, then we can carry out the reaction of the two and one can get the corresponding alcohol here with the double bond being here. That means the reaction takes place at alpha, beta and the gamma position. So, this is the gamma position, this is the beta position, this is the alpha position. But what about how can we carry out the reaction at the alpha position for example to get to a molecule like this or a molecule like this. That means depending on which direction, say for example if this happens to be R1, and then of course you will have this as R1. But if it wants to get something like this from a trans crotile substrate or a cis crotile substrate, then or we have something like this. So, with how are we going to get it, that we will look at it little bit later. Now, there are many other substrates which are very important, like such as allyl silanes. So, if we have an allyl MXN bond, then if we react with say chlorotrimethyl or any other silyl halide or triflate whatever, then we can get the allyl silane. And if we react with this R2BOMe, then we can get the corresponding allyl boranes. If we react with trimethyl trimethoxyborane here for example, then we can get allyl boronate, and if we react with the tin X, then we can get the allyl stannane. So, we have allyl boranes, allyl boronates, allyl stannanes and allyl silanes, and reacting with any one of these substrates where lithium, magnesium or potassium is generally used. Of course, you can also exchange these particular methoxys by other alcohols, and accordingly one can prepare these types of boronates. So, these various kinds of such allyl substrates have been utilized in the organic synthesis, and these are some of the very popular reactions in which the silicon, tin and boron based reactions have been utilized it. Now, what happens is that when we have an allyl silane, then you have to have a very strong activation, because the carbon silicon bond here is fairly strong and covalent bond, and it is not possible to react the double bond with any electrophile unless it is strongly activated. We will study about that a little bit later. Allyl stalanes on the other hand react upon heating or in presence of moderate Lewis acid activation, because carbon silicon versus carbon tin bond, the polarization is somewhat different. Allyl boranes can react with aldehydes in absence of activators even at -100 degrees. So, allyl boranes are extremely reactive, and on the other hand allyl boronates can react with aldehydes at room temperature in absence of activators, though they are slow. So, as you can see that each one of them has some merit and some demerit. So, we will look at the reactions of some of these and see how they lead to different products under different conditions. Now, if you look at the crotile metals, then crotile metal somewhat like this can be written up is in equilibrium with this, and it is found that if MXN, that is the metal, is either MgX or lithium, then there is a fast equilibration. On the other hand, when this is a potassium here, it is supposed to be going via a slow equilibration. So basically what is happening is that MgX or lithium plus could easily coordinate with the double bond and undergo rearrangement. So that means if we start with a cis double bond here, and it can be in equilibrium with the trans double bond. Obviously the trans double bond is more stable, and therefore many reactions proceed via trans products. But if we start with a potassium metal containing substrate, then it does not undergo equilibration that fast, and therefore we can stop it. For example, here if we deprotonate this particular olefin using a combination of potassium tertiary butoxide and N-butyl lithium, which is supposedly called as a super base, because the tertiary butoxide interacts with lithium plus, and then you generate a strong base as N-butyl minus, and that takes the proton away from here and it forms a potassium salt of the corresponding anion. And if now we react it with this trimethyl borate here, then we can get the corresponding boronate here. Now here the double bond geometry is retained. So all throughout the double bond geometry is retained. On the other hand, if we start with the trans double bond, then of course we can also retain that in the substrate that is obtained in the end, that is the boronate. Now if reaction is carried out with the aldehyde, for example here, then what is obtained is something like this here, that goes in here, that goes in here, and that comes in here, and that is how one gets the corresponding substrate product as it is here. On the other hand, when it is cis, now here Y and MXN are trans to each other, and that is what is happening here. Now as you can see that when they are cis to each other, this syn product is formed, and this is anti product. But interestingly, this is not formed with this, and this is not formed with this. So that means it is a highly stereo specific reaction. So if we take these two, we get this product, and if we take these two, then we get this product. How does this reaction occur? We will discuss it about it through the various transition states that we can think about it.
But before that, as you can see, we have some examples. If we start with an aldehyde of this kind and react with the allyl boronate of this type, in which the double bond has a mixture of E and Z isomers, in which the E isomer is dominating, that is 90:10, then when the reaction occurs, we get the corresponding homoallyl alcohol as the product, in which the anti-syn ratio is 98:2. That means anti product is the major product. On the other hand, if we start with an allyl halide or allyl substrate of this kind, in which the double bond is cis oriented, and react with chromium chloride, then what happens is initially there is an oxidative addition to form this kind of chromium species, which still has that double bond in the cis orientation, but then it undergoes fast equilibration to the chromium species of this kind, in which the double bond now has become trans oriented, which can also be obtained if we start with the corresponding trans allyl starting material instead of cis allyl starting material. Then we get this mainly as the chromium species having the trans oriented double bond. Now this particular trans oriented double bond containing chromium species then reacts with the aldehyde and leads to the formation of the anti homoallyl alcohol as the major product. Now the way reaction works is this chromium species interacts with the aldehyde, where there is a chelation between chromium and the oxygen, of course, and then there is a CC bond formation here, leading to the expected homoallyl alcohol as the major product in anti stereochemistry, as shown here. Now, how do these reactions of allyl boronates proceed with aldehydes? Then we can look at it carefully in what is the transition state. For example, if we start with this allyl boronate in which the double bond is trans-oriented and react with, say, benzaldehyde followed by basic workup, it leads to the formation of the corresponding homoallyl alcohol, in which the syn-anti ratio is 5:95. That means the anti-product is a major product. Now we look at the transition state, which is like this, in which the benzaldehyde is oriented in such a way that the phenyl group is equatorially placed, and then the oxygen interacts with the boron of the allyl boronate, which has a trans double bond as shown here. In this condition, then the carbon-carbon bond formation takes place, and of course that leads to the formation of the anti as the major product. Likewise, if we start with the cis allyl boronate, then we get the corresponding homoallyl alcohol as the major product, in which syn-anti ratio now is 94:6. That means now syn product is the major product. Again, we can write the similar type of transition state. We write that the benzaldehyde is put in such a fashion that oxygen, of course, chelates with the boron, but the phenyl group again remains in the equatorial position. Now, the products that are formed from these two transition states could be written up like this here, as a sawhorse projection or a Newman projection or in a zigzag fashion. And also from here we can write a similar type of orientations of the product. Now we will stop it today, and we will look at some of the aspects of these types of reactions next time.
Till then, bye and thank you and take care. We'll see you next time.